Hey everyone, and welcome back to HQRS, where we unravel the universe's most mind bending phenomena. Imagine this: you're trying to throw a ball over a wall, but you don't have enough strength. What happens? It bounces back, right? Now, imagine that ball, without gaining any speed or force, simply appears on the other side of the wall. Sounds like pure magic, right? But is, in fact, the bedrock of quantum physics. This is the core mind bending truth of the quantum world. We are talking about quantum tunneling, and this year, the groundbreaking research enabling us to harness this impossible feat has been recognized with the prestigious 2025 Nobel Prize in Physics. Now, let's begin with what we think we know. In a macroscopic world, that is, the world we can see and touch, objects behave according to the principles of classical physics. If you throw a tennis ball at a brick wall and it doesn't possess enough shear force or speed, it simply rebounds. It cannot pass through. The wall represents an energy barrier, a physical obstacle that requires a certain amount of potential energy to overcome. If the ball's kinetic energy, that is, its energy of motion, is less than the barrier's potential energy, passage is strictly forbidden. It's a simple, unyielding rule. But now, let's shrink down, far beyond what the human eye can see, into the realm of the subatomic, the infinitesimally tiny world of electrons, protons, and elementary particles. Here, the elegant and intuitive rules of classical physics crumble, giving way to the stranger, probabilistic laws of quantum mechanics. At this scale, these tiny particles routinely perform feats that would be impossible in our everyday experience. They can approach an energy barrier, say a small localized region of high electric potential, yet despite possessing insufficient energy to classically surmount or break through it, they inexplicably appear on the other side. This truly astonishing phenomena is quantum tunneling. To grasp how this impossible passage occurs, we must fundamentally alter our perception of these subatomic particles. They are not merely tiny localized balls. Instead, in quantum mechanics, particles exhibit wave-particle duality. They behave simultaneously as both a particle and a wave. This means they aren't just little dots flying through space. They also spread out like ripples in a pond. Before we look at them, they act like waves, flowing through multiple paths and creating patterns like water does. But the moment we try to observe or measure them, they appear as tiny, solid particles in one spot. It's not that they switch between being a wave or a particle, they are always both. Their wave nature tells us where they might be, and their particle nature shows up when we check closely. Like a secret that behaves differently depending on how you ask, quantum particles reveal different sides of themselves depending on how we look. Crucially, they are described by a wave function. Now, imagine a particle not as a tiny marble but as a continuous wavy rope that stretches through space. This wavy rope is the wave function. The height or intensity of the wobble at any point along this rope, that is, its probability amplitude, tells us the likelihood of finding the particle at that specific location. Where the wave is high, the probability is high. Where it's low, the probability is low. The particle's existence is a spread out possibility, not a fixed point. Now, this wavy rope, a quantum particle, approaches a solid wall, which is a potential energy barrier. Classically, if our rope doesn't have enough energy to clear the wall, it simply stops at its base. But quantum mechanically, the game changes. Even if the particle's energy is less than the barrier's height, a remarkable event unfolds. A part of its wobble, its wave function, doesn't abruptly terminate at the barrier's edge. Instead, it penetrates into the barrier itself. Think of it like a ripple in a pond that, instead of stopping at a submerged log, continues to ripple through the log, though becoming much weaker on the other side. Inside the barrier, the probability amplitude, the wobble of a rope, decays exponentially. This means the probability of finding the particle within the barrier rapidly drops off. However, here is the crucial counterintuitive part. If the barrier is sufficiently thin, meaning a narrow potential well, or sufficiently low, which means a small potential energy difference, that tiny attenuated wobble, that incredibly small residual wave function, can actually extend all the way through and emerge on the other side. If this attenuated wave function, this tiny whisper of probability, successfully permeates the entire barrier and emerges on the far side, then there is a small but very real non-zero probability that when we try to observe or measure the particle, it will suddenly be detected on the other side. The particle didn't gain energy, it didn't teleport, it didn't physically pass over the barrier. Instead, its intrinsic wave nature allowed it to tunnel through it. It's a fundamental statistical outcome dictated by the Schrodinger's equation. This phenomena is dictated by several factors: the height and width of the potential barrier and the mass and energy of the tunneling particle. Thinner, lower barriers and lighter particles with less mass exhibit a higher probability of tunneling. This seemingly impossible quantum feat isn't just a theoretical curiosity confined to textbooks. Quantum tunneling is a critical, pervasive process fundamental to both the largest cosmic structures and the most intricate pieces of modern technology. For example, without quantum tunneling, the Sun, and indeed every star in the universe, would cease to shine. The energy that bathes our planet in light and warmth originates from nuclear fusion, a process where atomic nuclei combine. For fusion to occur, two positively charged hydrogen nuclei or protons must get incredibly close, overcoming the mutual electrostatic repulsion known as the Coulomb barrier. The temperatures and pressures inside the Sun are immense, but they are not high enough for these protons to classically overcome the Coulomb barrier. They would simply repel each other. It is solely due to quantum tunneling that these protons have a small but vital probability of tunneling through that formidable repulsive barrier and fusing together. This process releases the colossal energy that defines a star. Our very existence, the warmth on our skin, the light in the sky, all thanks to quantum tunneling. Quantum tunneling isn't just a cosmic phenomenon. It's deeply embedded in the electronics we use every day. You might have heard of flash memory and SSDs, right? They rely on tunneling to store data. Electrons pass through an ultra-thin insulating layer and get trapped in a floating gate, changing the electrical state to represent binary data, which is zeros and ones. Without this tunneling, your phone, USB drive, or computer wouldn't be able to retain information. STMs, or the Scanning Tunneling Microscopes, use a sharp tip placed extremely close to the surface, and electrons tunnel across the tiny gap. And the resulting current is used to map atomic scale features. This technique revolutionized nanotechnology and earned its inventors a Nobel Prize. So yes, quantum tunneling is not just a theoretical curiosity or a stellar engine. It's an invisible but indispensable force driving the digital world around us already. In 2025, the Nobel Prize in Physics honored a stunning leap. Scientists learned not just to observe quantum tunneling, but to control it with precision. By crafting ultra-thin layered materials, they could shape the barriers that electrons tunnel through, like sculpting invisible walls at the atomic scale. This breakthrough unlocked ultra-fast quantum processors, ultra-sensitive sensors, and entirely new kinds of electronic devices. What was once a strange quantum trick is now a powerful engineering tool opening the door to a future built on the rules of quantum world. If this journey into the quantum realm left you amazed and ready to explore the impossible, hit that like button and subscribe to HQRS for more.